Hello everyone, welcome to grade 8 integrated science at the junior school. We want to look at something on force and energy, that is a strand, and the substrand, which earlier on I talked about, that was the subtopic in secondary school. And the substrand there is pressure in liquids. Pressure in liquids. We want to look at how can pressure be evaluated in liquids. We have some very important points that we need to understand when it comes to pressure in a liquid. And we have two factors which are actually depends or which pressure in liquids is depending on. And these two factors is actually the density of the liquid. That is the first one. And the second one is the depth of the liquid at that point. When you talk of the depth, we mean the height of the liquid at that particular point. And we have a very important point that we need to note, that the depth of the liquid is also referred to as the column height of the liquid. It is also referred to as the column height of the liquid. Now, the pressure at the point in a liquid can be expressed as H rho g, or we term it as rho gh, where rho, that symbol there, is for density. The symbol rho is for density. That was in form 1. The g is the gravitational pull. That is the gravitational pull, which is always 10 Newton per kg. 10 Newton per kg. That is the acceleration due to gravity. Then h is the column height of the liquid, or we call it the depth at that particular case, the depth of that particular liquid, Now, having known the factors which are affecting pressure in liquids, we want now to look at how can we derive this particular formula that we are talking about, H rho g. Where does this H rho g originates? So that is how to derive the formula for pressure in liquids, which for that case is H rho g or rho gh, depending on how you can rearrange the factors there. Now, to derive this formula, we are supposed to consider a cylindrical container with a cross-sectional area A and the height h, which is being filled with a liquid of density rho. That container is there. The container has got the height. That's got the height there. We also have the liquid being placed inside here, or put inside. That is the liquid which is having the density rho. For that case, the density there is rho. Now, we all know very well that volume of any given liquid, the volume of any given liquid is a cross-sectional area, then times the height. Cross-sectional area times the height. The height is h. The cross-sectional area there is cylindrical in shape, so therefore it is pi r square. Pi r square. That is a cross-sectional area, that circular part. Then now times the height. So in that case, in short form, it will be AH. This value here, the AH. And we also know that we need also to get the mass. The mass of the liquid, remember, mass is the density times volume. That was in measurement form 1. So mass of the liquid is the density times the volume of that liquid, which for that case, it should be the rho, which is the density here, times the AH. AH was initially there, which was the volume. So AH is the volume, and this is the density. After getting the mass now, we are supposed to get the weight of the liquid column. We want to get the weight, and we know that weight is the mass of the liquid multiplied by the gravitational pull or acceleration due to gravity, which is in that case will be given by mg. It will be given by mg. But now mass we had already obtained in the second equation there, which is a rho ah was the mass. So it is only now to add g to get the weight. So this is the weight of that particular liquid at the column height h. Now under the definition of pressure, we say that pressure is a force acting perpendicularly per unit area. So therefore pressure will be now the force all over area, but we know that very well that force is also the same as weight of that liquid. So for that case it will be weight of the liquid column divided by the cross-sectional area. All those dimensions we have rho ahg, that is the mass or the weight of the liquid, then divided by the cross-sectional area for that case, which in this case now be the area and the upper side will cancel, so area and area will just go. We remain with rho gh. So that is how the formula is being arrived at. That is how the formula is being derived. So when you see this formula, this is a formula for pressure in liquids, and it is applicable to any liquid which is having a density for that case. Now we also have a single example here which is trying to explain what our formula is all about. The example is here. We have been told that figure 3.27 has 2 points, or shows 2 points, x and y. I think you can see that at the depths x or hx and hy respectively in water. So it is placed in water, given that hx, that is the height x, is 24 centimeters and the height for y is 45 centimeters. Then the question is, determine the pressure exerted by the liquid at point x and y, So therefore we need to know very well that the only formula we can apply is the one that we have there, that is pressure is rho gh, or rho hg, depending on your arrangement. So therefore if you want to get the pressure at point x, that is a pghx will be the same as the density. Remember, it has been placed in water, so which means the density of water is always 1000 kgs per cubic meters or 1 gram per cubic centimeters. But remember, pressure is in Newton per square meter, so which means we are supposed to change the 1 gram per cubic centimeters to 1000 kgs per cubic meter, which for that case, this is where this 1000 is coming from. 10 here, the 10 value here is the value of gravity, that is acceleration due to gravity, which is 10 Newton per kg. Then times the height. So the height should be in meters because the density is kgs per kgs per cubic meter. So therefore, the height should always be in meters for you to get. So this one is in meters. And when we evaluate the pressure at point X is 2400 Newton per square meter, or 2400 Newton per square meter. Then we have the pressure at point Y. We do the same. Pressure at point Y will be BGH, and not B but rho GHY. rho GHY. The density doesn't change because it is still in water, so it should be 1,000. It should be 1,000 multiplied by the gravitational field strength, which is 10 Newton per kg, then multiply by the height. So the height there was in centimeters, so you divide by 100 to meters, which for that case, when you evaluate there, you get 4,500 Newton per square meter, or Pascal, You can also say Pascal is the pressure for that case. Otherwise, have a nice time, guys. I'll see you.